So chapter 3 is about logic. And I'll talk a little bit more about why we're covering this at the beginning of section 2. But for right now, we're just going to introduce some terminology which has some similarity between what we did with set theory. So logic consists of, I'll give an example of where you might use logic in your everyday life. So if it is Saturday night and I have $20, then I'm going to go to the movies. Okay, so that's a logic statement. And if it's true, it's true that it's Saturday night, and if it's true that I have $20, then the result then the result is that I'm going to go to the movies. But if it's not Saturday night, the logic statement is true if I satisfy the first and second requirements, and therefore I'm going to. But if it's not Saturday night, or I don't have $20, or if it's not Saturday night and I don't have $20, if any of those three combinations are intact, then I won't go to the movie. So you have to have. So that's an example of a logic statement. So like we do in math, we normally use symbols to represent something. In algebra, we usually let x represent the x coordinate and y to represent the y coordinate in a Cartesian coordinate system. So when we said plot, x equals 3, y equals 2, we were really plotting the x coordinate on the Cartesian plane is this, and the y coordinate in the Cartesian plane is this, and then we knew what to do, and so we had a short way of doing it, and then we had a long way of doing it. So we have the same thing in logic statements. And we're going to use, so what we're going to use is what's called symbolic logic, where we use letters to represent statements like, it is Saturday night, I have $20. And we're going to use symbols to represent words such as and, or not. And the restriction on symbolic logic is it only deals with statements that involve facts. What that means is you can either answer it with a yes or no or a true or false response. So if I were to say, what day of the week is it, that would not be a statement because I have 7 days of the week, and I can answer it with 7 results. If I said it is Saturday, then it's either Saturday or it's not Saturday. So that's an example of a statement versus, so it's either true or not true, false or not false. So the statements are just declarative statement. Just a statement in logic is a declarative statement in English that is either true or false, but not both simultaneously. So I use the example, you can be alive or you can be not alive. You cannot be half alive. What's that? Schrodinger's cat. Yeah, well that's, Schrodinger's cat. Yeah, that's probably, that's quantum mechanics. So, so what we're going to do is we're going to look at some statements, see whether we can call them, if they fit the requirements to be a logic statement. And then we're going to take statements together and represent those by a mathematical expression using symbols instead of words. That's kind of the gist of what we're doing in this first section. So the first thing, you've got a couple of homework problems which ask you to determine whether a series of words or equations is a statement. So there's 3 examples. The zip code for Oscar, Louisiana is 70762. So so we ask the question, can that be answered by a true or false? We don't know if it's 70762, but we can answer it. We can go to Google and check it out and see whether that's true or it's false. So the first one is an example of a logic statement because it can be answered in a true or false response. So we would say, can it be answered true or false? That's the question we ask. And if you say yes, therefore it is a statement. It doesn't have to be true. It just has to be able to be answered true or false. So, for example, the next one actually consists of two statements with an or in between, but we'll treat it as a single one. So 5 plus 9 is 14, which is not equal to 12. So this is a fact. It's either, in this case, it's a true fact. The second one, 4 minus 2 is equal to 5. Well, 2 is not equal to 5. It's a false statement, but it is, again, it's a statement because I can say this is either true or false. It's either equals or not equals. So because of that, even though I have this connecting thing here, this connecting word, this really consists of two statements. So I'll say this consists of two statements. So I'll just say the result is a logic statement. It has a special name, which we'll tell you what it is in a second. So if you have parts that are statements, the totality is a statement. Whereas the last one, where are you going tomorrow? So if I said, where are you going tomorrow, and you said true, that would probably, people would think you're crazy. So this, you can answer the question, but there's 7, well, where are you going? There's an infinite number of things that you could answer. So because you can't answer it in a true or false, it's not a logic statement. It doesn't have to be logical. It just has to be a statement that could be answered true or false. Logic doesn't have to be logical. Okay. Now, if you take two statements and you combine them with a connective term such as and, or, not, or also if-then, we've used the if-then thing just a minute ago, using any of these 4, 1, 2, 3, and this is considered 4. If you use any one of those connective words between two statements, then it's called a compound statement. So this would be a compound statement because it has the or. My original thing about if it is Saturday and I have $20, it is Saturday is a statement, I have $20 is a statement, and combining those with the and is a compound statement. I mean, you don't have to have you could say, if it's Saturday, then I'm going to the movies. It doesn't have to be, if-thens don't have to be compound statements. And then there is what's called a negation. And a negation just means that if you have a statement, whether it's true or false, the negation of the statement is the opposite truth value. So if I said let's say it is Monday, that's a true statement. So the negation of that statement is it is not Monday. Now if I said it is Saturday, that's false. So the negation of it's not Saturday is that it is Saturday. So just when you have a negation of a statement, a false statement becomes a true statement becomes a false statement. You got to be careful about how you word it so that it is the opposite. There are cases which we'll look at where it's not quite, you can't always just put a not there. It doesn't always work. Okay, so we've got, yeah, that's all we need to talk about right now. Okay, so they have a couple of problems, ask you whether a statement is a compound statement. So tomorrow is Saturday is a statement. It can be either true or false. But because there is no additional word like and or not, well, actually not is not one of them. And or, I guess not, they do put that in there. That's interesting. I'm not sure if I agree with that or not, but we'll come back to it. Just putting a not there doesn't necessarily make it a compound statement. So anyway, because there is no connective and or if then the first statement is not a compound statement, so just a single statement. So I'll just say only one part, therefore not compound. Whereas the second one, if Lori Morgan sells her quota, then Michelle Cook will be happy. So we have one statement here, we have a second statement there. It's connected by this if-then arrangement. So because it's using this, because there's more than one part, and because we have if and then, this is a compound statement. So it's for two reasons. There's two parts, and also we have the if-then arrangement. Sometimes the if-then is implied, so you have to be careful. You can't just look for the words if-then. So we'll do that. We'll do that later too. Okay, so that's compound statements. And then we need to be able to write an appropriate negation of a statement. Most of the time, using the word not is appropriate, but there are some cases where it's not appropriate. So her aunt's name is, I always pronounce this wrong, Hermione. Okay, Hermione. Okay, her name is Hermione. So the negation of this statement, there's two. I'm going to give you two examples. Her aunt's name. This is where you use not. Aunt's name is not. Hermione. Okay. You can also say it is not the case that her aunt's name is Hermione. You're thinking, why did you, that seems like you're overkill. Why not just use the word not? Because if ever in doubt, use the second case. If you write, it is not the case, and then write the original sentence, that always works, even though it is kind of a lot of words that may be unnecessary. And that's the second case. The second case is one where you can't just put a not or a no without really thinking about what the consequence is. And this, we'll talk about this in just a second, but there are certain words, like all, that to take the negation of all is not a simple matter of putting a no or a not. So what a lot of people will do is they will say, what's the opposite of all? None, right? That's what most people would think. But there's all, there's some, and there's none. So how do you take into account some and none? Because all means everybody. And so any case where it's not everybody, then you have to include that in the negation part of it to be accurate. We'll come back to this one because we're going to talk about it in a little more detail. So it's not obvious. That's the thing here. All students. You could write, it is not the case that all students. Okay, that one would work. But a shorter version is sometimes more difficult to come up against. And typically on the test, I'll give you an easy one like this and then one that's not so easy. Okay, so we will come back to that. Now, these connective words that we use, and, or, and not, have symbols which sort of look like the ones we use for set theory. And we use the word and for intersections. We use the word or kind of in a union sense. And not, we used, what did we use there? It was the complement. So in set theory, it was intersection, union, and complement. In logic theory, we use and, or, not. And the symbols, you know, for a intersection, we use that upside down U-ish like thing. Here we use an upside down V. So that represents the word and. And then the V represents the word or. And the little tilde, or squiggly, we'll call it probably squiggly just because that represents negation, whereas in set theory we have the prime, which represented the complement. So and then they have special names too. So a compound statement with two statements connected by an and is called a conjunction. A logic statement connected by an or is a disjunction. And a statement that is negated is called a negation. So what we're going to do is we're going to use letters to represent words, and we're going to use symbols to represent these logic, we'll call them operators. So here's a couple examples that you have to do for the first section. First section is pretty easy. The second section gets a lot harder. So enjoy it while it's easy. So what we have here is we have a tilde. Let me put this on one page so it's a little bit bigger. So we have a tilde, which stands for negation, and we have Q, which stands for the statement, he is as old as dirt. So this logic statement represents the negation of statement Q. So we have to look at statement Q and come up with, add a not if appropriate. So he is as old as dirt, then the opposite, well, the negation would be he is not as old as dirt. Okay, so to answer this question, we just write out he is not as old as dirt. Or it is not the case that he is old as dirt, but we can use not in this case. Okay, so that's the first one. The next one. So we have a negation of statement P. This is the or statement and statement Q. So all we have to do is go back up to the different two statements. So we're going to write the negation of statement P, which he has one bad eye. So the question is, what is the negation if he has one bad eye? So if you had two bad eyes, would the statement he has one bad eye be true or not? Does that cover having one bad eye? It doesn't tell you which eye it is. He doesn't say it has one bad left eye and one bad right eye. So if he has one of them bad, then that is a part of his true statement. But if he has both eyes bad, I think it's still true. What's that? He still has one bad eye. There's also, yeah, he has another one right beside him. So the case of negation here would be, you could say he has two good eyes, or it is not the case that he has one bad eye. So either one of those, I guess, or he does not have, because if you said he does not have one bad eye, two bad eyes would be, that wouldn't, I mean, that's that he's either saying he has no bad eyes or he has 2 bad eyes. So that's why you wouldn't want to use just he doesn't have 1 bad eye, because it wouldn't be. So I'm going to say the answer is he has 2 good eyes, or he is as old as dirt. Okay, so that's that one. Pardon me? Oh, the question? Oh, yeah, the question was this. There was no question. What we're doing was we wanted to write a statement, write out in words what this represents. So it's this negation P or Q. So I did a negation of statement P, which was he has 1 bad eye. So that I decided that the negation of that, he has 2 good eyes. This represents the or, and then statement Q is directly from up here. He is as old as dirt. So you just copy. When you have just the statement by itself, it's easy to just copy it down. Let me put this there. Okay, the third one is the negation of P. We've already done that, and the negation of Q. So this is just a matter of putting together what we've already figured out. So the negation of P was the statement he has 2 good eyes. This upside down V represents and the negation of Q is he is not as old as dirt. So it's just a matter of, they don't have to be true. The logic statements don't have to be true. We just have to be able to translate between words and symbols. And then the last one is this one, which I'm going to write on the next page so we can see. So it's this statement with another negation in the front of it. So let me just write it down. Oh, those little things on the screens? I don't know. Now that I know that it bothers you, I gotta fix this one here. It's blurry. Yeah, that's one reason. I kind of had ignored it because it was blurry. And this, I see the thing over here too. It says make call. Is that what it says on the bottom? Yeah. Yeah. Usually, what happens is if you use compressed video and you're calling the other thing, school, you'll push make call, and I'm afraid to do that because I really don't want to make a call. I just want to leave it alone and just stick with that up there. So I'm going to tell you a short story about bad eyes. So I wear these glasses which are very thick on one side, very thin on the other side, and they're opposites. And the reason I do that is because it's about 3 or 4 years ago, we were on vacation, and I started seeing double vision, which is kind of scary, especially when you look it up online and they say, if you're starting to see double vision, you should go to the emergency room immediately. We were planning on, we visited Jennifer in New York, and then we were going to go to Maine. Has anybody been to Maine before? So we're going to go to Maine, Portland, Maine, and then we're going to go up to Acadia National Park, which is up in Maine. So we were camping out. We were camping in both locations. So it actually started bothering me when we were visiting in New York, but I tried to ignore it like a man. And then ultimately, since it lasted more than a couple of days, I decided to look it up on the internet. So the campground we were at had Wi-Fi. If you were drying your clothes, I couldn't get it to the campsite, so I walked up there with my computer. I check it and I go, you should go to the emergency room immediately. So I go back to the campsite. Martha, I just looked this up online, and this is what it says. So we called our daughters to tell them that we may be cutting our vacation short. Jennifer wanted us to come to New York instead of going back to Virginia. Anyway, we ended up driving the next day back to Winchester, Virginia, because that's where our families are from. And I'd already searched on the internet because it was a weird thing. It was double vision, but if you tilt your head one way, it's not as bad as if you tilt your head the other way. So if you search for double vision with head tilt, you'll get a diagnosis. And so, make a long story short, went to the emergency room. They did an MRI. They said, you know, you don't have a tumor and you don't have an aneurysm, which is good. But we think you have this problem. And I've been to ophthalmologists, neuro-ophthalmologists. Every time they've said the same thing. So my original diagnosis was actually correct. And so anyway, I've got these big prisms in my glasses. So I have one bad eye, which is the one I close when I take my glasses off, and one good eye. And the only advantage is that I never forget my glasses, because when I look at you guys, your heads are about this far apart. About this far apart, depending upon how close you are to me. And these glasses fuse, so I can't even figure where my fingers are, because I've got two sets of fingers that go like this. It's really weird. What's that? Yeah, no, it's never going to get better. So it's kind of one of those things you go like accept. Well, actually, it's interesting. So you can get the surgery done to your eye. What they do is, the problem is that the nerve from my brain to my eye muscles is screwed up for some reason. They don't know why. So what they do is they take the good eye and make it as bad as the bad eye, so that they both track the same position. So, but to me, doing surgery on your eye muscles, and then, whoops, we went a little too far. Whoops, I don't know how close I can get. So I figure wearing glasses is better than taking any chances of getting surgery to it. So anyway. So what you do in this case is, since we pretty much have the original statement, this additional negation would be, it is not the case. So the negation I'm just representing is not the case. And then I go back here to where I've already done this. It is not the case that he has two good eyes, or he is as old as dirt. So when you have a negation on the outside of a parenthesis like this, where these are grouped together as a complete statement, you can do this additional negation. You wouldn't want to say, it is not the case that is not the case. That would get confusing if you did the negation. So that's why it's, in this case, this negation could be represented by this statement, and then we use the not the case one time, and it's okay. Okay. And then you go the other direction. You have a statement, and you have to rewrite it in some symbolic form. So we have the two statements written out again, and here's the words. So basically all you have to do is determine whether the part of the compound statement is the original statement, then it's just the letter, or if it's the negation of the statement, then you put a little tilde in front of it. So this first one is, John is a bass player. So we look up here, John plays the bass guitar. They're the same. Slightly different words, but they're the same. So we're going to put that as P. That's just statement P. we use the upside down V to represent the word and Jill is not a genius compared to the original statement. Jill is a genius, so Jill is not a genius is the negation of statement Q. So that is the symbolic form of that written statement. Now, the second one is a little more difficult because this is kind of like it is not the case. Neither is John a bass player, or is Jill a genius. So what we can do is John is a bass player or Jill is a genius. We can represent that, and then we can put that in parentheses and put a negation out in front, because this neither is referring to both statements. I guess it'd be neither nor, either or, so maybe that should be an or. Pardon me? Neither is John a bass player, nor is, but you need it. Can you get by without it? Neither is John a bass player or Jill. Yeah, you wouldn't necessarily need it. Yeah, you can get by with it. So this case, without the neither on there, you would have John is a bass player, which is the same as the original statement. Jill is a genius, which is the original statement. I'm using the or, so I would use this upside down V, and then I would put it in parentheses with the negation out front. So that's another way of representing a negation. The easiest way to do it is this way, and this is what I'd expect. If you ever have to go the other direction, just say it is not the case. I guess so let's think about that. Neither, so if we did neither does he have two good eyes, nor is he as old as dirt. I guess that would be the way you would use neither nor instead of just it is not the case. That's a little harder to think about. Okay, so you got a couple of those to practice on. Now, we didn't finish that one problem because we need to talk about this use of words other than just a statement about an individual thing, he, she, whatever. So there are certain quantifiers like all, each, every, and no. And they're called universal qualifiers because by using those words, you're not saying a particular person or a thing, you're talking about everything or nothing. And there's something in between everything and nothing that's, some, one way or the other. So the other qualifier, these are called universal qualifiers because they're everything or nothing. Whereas you have the word some, and for that, some, they could be from one to one less than all. So when you have statements that involve these particular words, you have to be careful about how you make the negation. You can always use it is not the case, which may be not pleasing English-wise. So what we're going to do is we're going to look at an example which is in your book. So you don't have to, you can just refer to your book. So what we have is a statement. All girls in the group are named Mary. So what is the negation of that statement? What we're going to do is we're going to look at the original statement, and we're going to look at whether these three groups, if you looked at this statement, whether these three groups are a true if these agree with the statement or don't agree with the statement. So if they do, then we say it's true. If it doesn't agree, we say it's false. And notice that the three groups have different characteristics. This one has where everyone's name is Mary. Here we have one of them is Mary. One of them is named Mary. So some of them are Mary. And this one, there are none that name Mary. So they give all that we have the universal cases, all Mary and no Mary, and we have the middle one, which is some, one Mary. It could be two Marys. It didn't really matter, just so it's not all or none. So if you look in your book, what you'll see is this table. And I'm going to put this on one page so you can see it better. So we originally look at the statement, all girls in the group are named Mary, and then we look at the groups and say, is that true or not? So the first case for group 1 is they're all named Mary. You can't see them, but I told you that. So it is true. In group 1, all of the girls are named Mary. In group 2, not all of the girls are named Mary, therefore it's a false statement. And finally, the last group, where none of them are named Mary, this statement, which is the given statement, is false. For a statement to be a negation, what used to be true becomes false, and what's false becomes true for all situations. So the first example of a possible negation is no girls in the group are named Mary. So we're using just the word no. None of the girls in the group are named Mary. So that's one possible negation. And then you look at the three possibilities. Well, in the first case, are none of the girls in the group, no girls in the group are named Mary? Well, they're all named Mary, so obviously that's a false. This is a false statement relative to the first group. Are no girls in the group named Mary for the second one? Well, there's one that's named Mary, so that means it's a false state. This is a false statement according to each one of those, to the second group. And then the final one, yes, that's true. In group 3, no girls in the group are named Mary, so this becomes true. And if you look at the first group, which has all Marys, and the last group that has no Marys, the false statement becomes true and the true statement becomes false. But the one where we have just one Mary remains a false statement for both the original given statement and our possible negation. So that's not going to work. We can't just put a no there. The next one would be all girls in the group are not named Mary. So rather than using no here as a negation, we're going to say not. That's another way of usually saying a negation. So again, we ask the same question and ask it for the three groups. The first group is all Marys. All girls in the group are not named Mary. Well, that's false because all the girls in the group are named Mary. The second one, all of the girls in the group are not named Mary. That's false because one of the girls in the group is named Mary. Only the last one is true because all of the girls in group C are not named Mary. So that's true. And again, the first and the last are opposite truth values, but for the second one, it stays they're both false. So again, that is a possible negation, but it doesn't work. So the final one that works is some. So the first group, so we'll say some of the girls in group 1 are not named Mary. Well, that's false because all of the girls in the group are named Mary, so some of them can't be not named Mary. So that's the first group. This is a false statement. Some of the girls in the group are not named Mary for the second group. Well, that's a true statement because one's named Mary, but 2 of them aren't named Mary. So that makes that true. And then the last group, some of the girls in the group are not named Mary. Well, all of the girls in the group are not named Mary, so that means this is true. Some are not named Mary. So we look at the truth values, and the truth in the original statement becomes false in the negation. The false in the original statement becomes true in the negation, and then false becomes true. So because all of the three possibilities have their truth values changed to false values and their false values to true values, therefore the last one is the appropriate negation. So if we go back to this other one, this other question here where we're looking at negations, wherever it was, here it was, all students present will get another chance. So all, what is the opposite? Well, we just, is it exactly what we had here? All girls in the group are named Mary. So we should be able to use the word some. Is that right? Yeah, I'm not sure if I agree with that. But that, let's go back to make sure I didn't do this. It's bothering me a little bit. Oh yeah, that's not, because this has some girls in the group are not named Mary. So there's a not, there's a some, and then there's a not. So that does not work. Some students present, I guess we could probably say some students present will not get another chance. That doesn't make sense. Okay. Yeah, that was the original one I was thinking of. I was trying to use that previous example, because usually I do it in this order. I do it this one first, and then I did the other one, and then I did the other one. I was like, oh, they're like the same. So you could say not all students will get another chance. Either one of those. Some students present will not get another chance, or not all students will get another chance. Because not all students means it could be none, or it could be one through not everybody. So here's kind of the negation of quantified statements. All do, some do not. That's what we kind of said. But I guess not all. That's kind of the same thing. And if you have a statement that involves some do, then the equivalent or the negation would be none do. Because some could mean all of them, or it could mean less than all of them, but some means at least one person. So the opposite of at least one person is none. So those are some ones that you could use kind of as a rule. And there's your homework for section 1. So it's pretty much what we did here. It's writing negations of statements. It's taking logic statements and making them into word statements, and taking word statements and making them into logic statements. The only probably difficult part is where you have these quantifiers like all or some. But I think this table 4 is probably a good, when you take the test, this might be something I would write in the test, because I'll typically give you an easy one and one that involves something like all or some. Well, what would be the opposite of, what would be the proper thing, negation of none? Yeah, but all would be, then so you want to, all condition, every condition that doesn't include none. So that could be all, but it could be some. So it's probably some. It's kind of the opposite here. None, the quantifier of the negation. So if you have none, the quantifier would be some. If you have some, then the negation quantifier would be none. You can go. I think you can go either way. So I think if you have some do not, you could go the other direction. So I think it's these statements are good either way. For none, go to some do. For all, go to some do not. From some do not, go to all. Yeah, this is due next Monday. Okay, so that's the one easy section in this. Now we're going to get harder because we can make these next things pretty complex. So James, you going to watch the debate tonight? Hillary and Trump? No. on what? Fox. Oh yeah, I know you're lying. Yeah, I'm interested to see how.
Okay, so this is your assignment to prove that you've watched the video. So what I want you to do is to write the negation of some students will watch this video. So that's the logic statement. Some students will watch this video. I want you to write the negation of that statement based upon what we just talked about.
I feel a little sad for the moderators because they're going to be, no matter what they do, they're going to be, somebody's going to say that they didn't do a good job. The question is, do the moderators fact check the participants? And the Republicans don't want to do that because Trump lies all the time. So the Democrats want them to fact check. The problem is, I guess, some people believe facts aren't necessarily true, which is kind of an that doesn't make sense. Facts, we're talking about facts here in logic. You know, there's truths or false statements, and so just because somebody says something a lot of times doesn't make something true. And not everything is relative, which is kind of ironic because, you know, typically conservative Republicans like to have black or white issues, true or false, but when it comes to Trump, he can say whatever he wants to do. Anyway. Okay, so section 2 is we're going to introduce truth tables, and they'll start out fairly simple, and then they'll become more difficult, much more difficult. So for each one of the for each one of the connective terms that we've introduced, the and, the or, the not, and if then, there are truth tables associated with those statements. And if you have a compound statement that involves an and, for the compound statement to be true, both of the statements have to be true. It's like with an intersection. To belong in the set that results from an intersection, you have to belong to set A and you have to belong to set B. Belonging means true. So if you're, from a logic standpoint, and means that both this has to happen and this happens to happen for me to give a particular result. So back to the movie theater thing. If it's Saturday and I have $20, then I will go to the movies. So for you to be able to go to the movies, it has to be Saturday, and you have to have $20. If it's not Saturday, you don't go. If you don't have $20, you don't go. And if it's not Saturday, and you don't have $20, then you don't go. You have only under one condition, where both statements are true, do you get to satisfy your appetite for watching movies. So when you construct a truth table, you look at it from that perspective. So what we have is we have two statements. If it's Saturday, I'm going to, I have $20. And so these first two columns are the possible combinations of things being true and false. So either something's true or false. So I can have both statements true. I can have the first statement true and the second statement false. That first statement false, second statement true, both of them false. The only one that gives me a true value, which means I get to do what I want to, I get to go to the movies, is when both the first and the second statements are true. So these are just all the combinations of true and false. It has nothing to do with logic. It's just a matter of populating your truth table with all possible combinations. For 4, it's always, so if you have 2 statements, it's always true, 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 false, false, true, true, false, false. So for conjunctions, conjunctions are when you have the conjunction statement or you have the word and. Both statements have to be true for a true result. I get to go to the movies. That's the result. Buying a house. I need to have a, if you have a good credit score and you have sufficient income, then you will get the loan. Do you have a good credit score but not sufficient income, then you don't get the loan. If you don't have either one of them, you don't get the loan. You don't get, it's either you get the loan or you don't get the loan. And truth tables have all the it says have all the possible combinations of true and false. That's what I'm talking about here. It's not just some random combinations. It's a very set list of, and it's kind of like subsets if you think about it. You know, the subsets that I could have. Yeah, maybe that's not a good example. Okay, so that's and. Then you have one for the or statement. Again, these little green boxes are in your book. So it's called a disjunction. It uses upside down V. For a disjunction to be true, you just have to have one or the other of the statements true. So if I said if it is Saturday or it is Monday, then I'm going to the movies. So if it's Saturday, I get to go to the movies. If it's Monday, I can get to the movies. If you know, you can have, that's kind of hard. You can't have both of those happening at the same time. But or if it's Saturday or I have $20, then I will go to the movies. So you don't have to have both of them true. If it's Saturday, I get to go to the movies. If it's $20, I get to go to the movies. If it's Saturday and I have $20, then I get to go to the movies. The only time I don't get to go to the movies if it's not Saturday and I don't have $20. So in comparison, you can see the difference in the truth tables. You get a true result for everything except when they're both false. Again, the first 2 columns are just true, false, true, 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 false, false, true, false, false. The truth table is what the result of this particular operation is. So you can write for disjunctions only one of the I guess I was hoping this was one word here. So there we go. For disjunctions, only one of the statements has to be true. Or you can say the only time a disjunction is false is if they're both false. That's the way I remembered. Either one, you know, you could say either just one of them has to be true, or or both have to be false to be false. And then the final operation we've been talking about, we'll talk about if-then in the next section, but the one we talked about so far is the negation. And the negation only consists of two choices because I don't have P and Q or P or Q, I just have P. So I have, let me put that on one page. The truth table for negation is that if you have a true statement, the negation of the true statement is false, and if you have a false statement, the negation of a false statement is true. So those are the three out of the 4 main truth tables for the operations. Now, I was going to explain why we're doing this. What's the purpose besides giving you guys work to do? Where does this stuff come into play? So I'm going to do a little. So this is to remind me what to do. So we're going to go over to Wikipedia. Okay, so computers. So we have these things, our smartphones or computers, that do all these neat things for us. We probably don't have any concept of what is actually going on inside those little chips, the central processing unit of these things. But ultimately, it all comes down to adding ones and zeros, believe it or not. It just blows my mind. But I guess it's like your brain. Your brain has things that can be either on or off in there, and we have consciousness. So if we can have consciousness, then I guess computers can do really amazing things. So what the binary system is representing numbers rather than 1 through 10, and then having the next digit, tens, hundreds, thousands. What binary does is represent quantities by just using ones and zeros. So we either have a 1 or a 0. And how does that relate to truth tables? Well, true you can consider to be a 1, and false you consider to be a 0. And in computer chips, 1 could be 5 volts, and 0 could be 0 volts. So you can actually represent trues and falses and ones and zeros in a computer by the voltage level. The voltage in our plugs here is 110 or 120 volts. So we're talking about, the voltage used in computers are much smaller, 5, 3 volts, something like that. So I'm going to demonstrate something here. Let me go back to, we'll come back to that in a second. So if you want to do some simple binary arithmetic, first let's see how we would represent numbers that we're used to in binary numbers. So this is going to be, we'll call this the decimal number, and we'll say this is the binary number. Okay, so what's the first decimal number? 0. What's the equivalent binary number? 0. The next decimal number is 1. The binary number is 1. Okay, so we've got two numbers that are the same. Now when we go to the decimal number 2, I can't use 2 anymore. So what we do is we just like when we go from 9 to 10, we add an additional. We use one of numbers from 0 to 9 again to help us move beyond 10. So the binary equivalent is 1, 0. So what I do is the ones column, the 1, 0 column becomes 0, and then I add a 1. It's just like if I go from 9 to 10 here. Here I've run out of numbers, so I go back to 0 and I add 1 in the next digit. So that's what I'm doing here, the equivalent, but I have to do it much earlier here because I've run out of numbers pretty quickly. If the decimal number 3, well, this has to be either 1 or 0, so the next option is to have 1s in both places. Just like I would go 10, 11, 12, 13, 14. Here I go 10, 11, but then I can't go to 12 because that's not allowed. So here I can go from 0 to 9. Here I can go from 0 to 1. Now 4, because I've run out of, I've gotten to the maximum number here now, I have to add another digit, and then I reset the other 2 digits. So those go back to 0. So that's the decimal equivalent of the number 4. and you keep doing it. So 5, you make this the first digit 1. Again, I can't go to 102, so I have to, for 6, I have to go to 1, 1, 0. So this becomes 0, that becomes 1, and then 7 would be 1, 1, 1. Okay, so what these are, you can think of these as almost like trues and falses. So that's what binary is, and that's how computers do all their calculations, is in binary. Now, the second thing you need to do, once you've represented numbers somehow, what's the simplest mathematical operation that we usually do? What's that? Addition, right? So how do you add, how do you do addition? So let's just demonstrate that. We'll do a simple case here. So let's say I want to do the equivalent. So here's the decimal again. If I wanted to do 2 plus 3, we know the answer because we memorized it is 5, right? If you look at it from a binary perspective, what we would do is we'd write down the binary equivalent of 2 and add the binary equivalent of 3, and we get some number like that. Now, what we're going to do is we're going to do it in column form. So we're going to have 1, 0, plus 1, 1. So the way it works here is just like normal math, you'd say 0 plus 1 is 1, right? And because 1 is not greater than, it's not the maximum number, well, it's not above the maximum number we can get, we put the answer here. So we add them columns. 0 plus 1 is 1. So let me just give an example over here. Let's say we have 34 plus 92. So here we add these two numbers together, you get 6. 4 plus 2 is 6. Then I add these two and I get 12. Well, 12 is more than 9, so I put 2 down, I carry 1, and then I bring 1 plus whatever that is, and I get 126. Okay, so you do the same thing for binary. 1 plus 1 is 0, because 1 plus 1 is 2, but I can't represent 2, so I make it 0 and I carry 1. And then I add these together. 1 plus nothing is 1. So my result is 101. So that's the binary answer. And if I go over here, binary 101 stands for 5, which agrees with what I got decimal-wise. So what's the logic here? Well, if I have a 0 here and I have a 1 here, I get a 1 there. So it's if this is 0 and this is 1, then my result is 1. It's an if-then statement. They're logic statements that you have to do. The other options, well, the other option was if this is 1 and this is 1, the answer is 0 and I carry 1. If this were 1 and this were 0, you get 1. So if this is 0, 1, or 1 and 0, you still get 1. If they're both 0 and you add them together, you get 0. So there are 4 different logic questions. If they're both 0, the answer is 0. If one's 0, then it's an if-then thing. If the first one is 0 and the second one is 1, the answer is 1. The first one's 1 and the second one's 0, the answer is 1. If they're both 1, the answer is 0, but you have this carry thing. So the whole process of adding, and it turns out the multiplication is very similar. Let's do multiplication just to show you it's not that really more difficult. So, you know, if I do 2 times 3, 2 times 3 equals 6. So from a multiplication standpoint, just like we normally do, except we're multiplying now. So what do? You take 1 times 0 is 0. 1 times 1 is 1. Then you put another 0 here because you're to the second place. 1 times 0 is 0. 1 times 1 is 1. Then you add these together. 0 plus 0 is 0. 1 plus 0 is 1. nothing plus 1 is 1. So the answer is 1, 1, 0, which is 6. So I got the same answer, see? So the multiplication is not that hard. And it's the same, it's a slightly different logic. You know, if this is 1 and this is 0, then the answer is 0. Whereas for addition, it was a different rule. If this is 1 and this is 1, then the answer is 1. So again, it all comes down to logic, simple logic questions. If, you know, with 1s and 0s, which are trues and falses. And so what I'm going to do here is I'm going to just show you something. So if you go down here and you look at binary stuff, it talks about how you deal with fractions. Here's talks about addition. What you have is, this is the actual electric circuit that is used to do the addition calculation. This is A and B are the numbers. They can either be 0, 1, or they can either be 0 or 1. This could be 0, 0, 0, 1, 1, 0, 1, 1. And they go into these electrical circuits, and if this particular electric circuit, if they're both 0, then you get 0 out here. If they're both 1, you get a 0 out here. If one is 0 and the other is 1, then you get 1 out. And there's a truth table. I think they show it here. There's a truth table for this particular addition logic. If I can find it here. I will write the truth table. It's not either one that we've done before. It's separate from it. So if I were to draw the truth table for the particular thing I'm just talking about, I would have this many entries. And so what we'd have is we'd have like P, Q, and P plus Q. I'm just showing it as an addition. And you'd have true, 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 false, false, true, false, false. Where true you can think of as a 1, and false you can think of as a 0. When they're both true, when they're both 1, you get a 0 result. When one's true and the other's false, 1 plus 0 is 1, you get one result. If one is 0, the other one is 1, you add those two together, you get 1. And if they're both 0, the answer is 0. So it's this truth table. So I'd say false, true, true, false. So it's a truth table. It's different than what we're doing. It has a special name. But there are truth tables associated with binary addition and multiplication. So what we learn here, for as far as logic is concerned, ultimately has to do with computers, how digital computers work, which pretty much rules our lives. And it makes you want, you know, sometimes scared about self-driving cars. Ultimately, that comes down, that complex decision comes down to adding ones and zeros. But it's also kind of amazing that you know, things. There probably was, but okay. So that's kind of why we're learning all this stuff. So what we're going to do next is we are going to get into a little more complex logic statements other than the three things that we've talked about. And so we're going to construct truth tables. And I'm going to start off with an example. And this is something we'll use here in just a second. But let's say instead of just P and Q or P or Q, let's say I had a logic statement in symbolic logic which was P and not Q. How do I construct a truth table for that particular slightly more complicated logic? So what you do is you create a table, and it turns out that it has to be this size, and I'll explain why it has to be this size in a second. So just like our truth tables for ands and ors, because we have both a P and a Q, we're going to have a column that's represented by the letter P and a column that's represented by the letter Q. And all truth tables require you to do this. In the past, we've just had a result. If we have something other than just P and Q and P or Q, we write out the new logic expression in the remaining spaces that we have. So this is the actual logic expression. This is just P and Q. Just like in the examples we gave, these first two columns are just the list of the possible combinations of true and false. So we just do exactly what we've done before. These are the four possible combinations of true and false. True, 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 false, false, true, false, false. So that's not any logic. That's just filling out some numbers. Then what you do is you take the truth values here, which are our possible combinations, and if it just has P, then you just copy the P column. If it has the negation of Q, then you take the Q column and you take the opposite truth values. So for this part of the logic statement, I'm just going to copy the first column because they're both P, so I can just write them both down. Whereas when you get a negation like this, you take the truth values that are in the Q column and you switch them. So the trues become falses and the falses become trues. So instead of true, false, the negation is false, true, false, true. And then the last step is you use this operator between these two columns. So you have to go back to the original truth table for the AND statement. So let me copy that over. And you probably want to copy these down on your test so you won't have to memorize them. And I accidentally copied it twice. So let me just finish this up so I have it complete. But what we do is we compare these two with the values in the truth table for the AND statement. So here I've got true and false, and I look down here for the same combination, true, false. The answer is false. The next one, I have two trues, so I look at the truth table. I get two trues. That means the answer is true. Here I have a false. Here I have a false. I look down at the truth table. That's false. And then I have a false and then a true, which is this entry, and I get a false. And that's my result. Okay, so we'll talk about on Wednesday what that means. What is the result of a truth table?